we looked at parametrizations or parametrized curves of the form x of t, y of t, z of t, for maybe t on some interval or just on the real line. And we looked at some ways to, well, there are two problems. First one was presented a curve in this form. How could we imagine it? How could we actually geometrically link what we've expressed algebraically, in a sense, to what the picture is in three-dimensional space? So given a parametrization, how can we picture it geometrically? And the methods here were, well, there were a couple methods here. The first one was, the overarching theme here is it's very, it's very difficult in general, right? There was an example where we did where, you could manipulate things algebraically and figure out where its projections lied on, or maybe x and y satisfies x squared plus y squared equals 1, in which case the whole thing must lie on some cylinder that looks like x squared plus y squared equals 1. And in those very particular cases, you could actually get a pretty good idea of what this thing looks like, right? So first method is see if gamma t satisfies any known algebraic equations. So for example, if given a parameterization, this is true, then gamma t must live on the cylinder x squared plus y squared equals 1 in R3, right? In this case, let's say here's a cylinder, and gamma t must somehow be confined to the cylinder in some sense, right? More generally, you could also look at its shadows, right? Can look at the shadows or projections of gamma t on the coordinate planes, right? So this comes from the method of looking at, say, eliminating one of x, y, or z, right? And that's just, if you imagine the plane here, I'm not going to draw it, but, well, maybe I will draw it in this case, say, right? That's just amounts to casting a light from up above or this side or maybe this side and seeing what image, what shadow this green curve casts. And then looking at the shadow, you might get a sense of, what the bounds of gamma t are, right? And you could say, let's say the limit as t goes to a, or limit as t goes to b, where the endpoints or domain are, to qualitatively see how gamma behaves, right? Last time we did our second example last time, I believe, we had a nice example of a curve that turned out to be somewhat like a helix. And that was because that was from method 1, right? In a lot of these cases you see in your textbook, on WebAssign, on, perhaps on the test, you should always try to see if any of the components satisfy some algebraic equation of a surface we know. Because if it does, then you know that your curve must at least live on this prescribed surface that we know. We know a few examples, right? Now the second equation, so the second curve we look at was much more complicated. It had a natural log term on one component. It had 1 over the square root of 9 minus x squared on the second component or something like that. And it lived, we prescribed the curve on a domain or an interval where everything was nicely defined. And we look at how the curve behaved as t approached either of the endpoints, right? And then we were able to confine our curve inside some kind of like a box, right? We were able to squeeze between two planes in certain dimensions. And we knew that we knew how to trap this curve in between certain dimensions so that it could never leave, right? So we didn't know precisely what the curve looked like, but we knew that it could not at least extend beyond certain limits. All right, so a couple of questions in chat. In B, we're supposed to take the limit as t goes to the start and terminal points. Well, it's often helpful to see how t behaves as its starting point and terminal point. So this might be minus infinity and positive infinity, right? Because then you could see which parametrizations are possible for your curve or not. For example, if, let's say, I have a curve that's x of t, y of t, and z. Let's do an example. Let's say if gamma of t has z of t is equal to, say, e to the minus t, and t is between minus infinity and infinity, what plane z is equal to k does a curve gamma need to above or below. And this goes to one of the questions in chat. This is, I mean, this is a very off the cuff question. I kind of just made it up, but something more rigorous here, but similar in spirit to this type of question, you'll have to be able to answer. All right. So in this case, maybe in chat, I could ask you, what are the bounds? Where must this curve be trapped? In this case, you have a curve gamma of t. I haven't barely given you any information on gamma of t, but I have told you what z of t is. Z of t is e to the minus t. Right. So in this case, I mean, clearly I don't want you to write z equals infinity here. So I'll make the question a bit, better. But the intuition is right. You can't, on the one hand, as t goes to minus infinity, as t starts at minus infinity, this is minus infinity. So roughly speaking, e to the plus infinity. Don't write this down, right? You can't really do e to the plus infinity, but you get the sense that at wherever t starts from back historically in time, it starts at a very, very high place, right? Z is very, very big. And then as t goes to 0, you end up at z equal 1. And then as t goes forward in time to infinity, this gets smaller and smaller and smaller until you asymptotically approach the plane z is equal to 0. And in this case, it actually doesn't ever approach 0. So there's a subtlety here. I mean, I can't say if your answers, you can't really say k is, well, so depending on how I phrase this question, you might want to be careful of your bounds, right? Technically speaking, k must be greater than or equal to 0, but even more strictly speaking, you must be strictly greater than 0, right? You could never actually reach the z is equal to 0 plane. So the answer here, I mean, so the qualitative answer is, let's say, as you take the backwards limit, e to the minus t diverges, does not converge, right? But it diverges to plus infinity. And as t goes to plus infinity, e to the minus t approaches 0. So that means that gamma t must lie strictly above the z is equal to 0 plane. So this is the type of behavior that you got to be able to understand from our discussion last time. Another fair question I could ask is, suppose I gave you another function, another parameterization of a different curve with possibly a different function z of t, but with the same asymptotic behavior in t. All right. So for example, I could say z of t is minus, if it's minus 1 over t, then, well, maybe I shouldn't, maybe that was too soon. So let's say if this were minus 1 over t, then you should also be able to deduce what the asymptotes here are. Well, in this case, you have to be strictly away from 0. Let's say t is, I'm just off the cuff here, but let's say t is always less than 0. Then, and if this were the case, then you should also be able to deduce the behavior that as t approaches 0, this gets more and more negative. Sorry, more and more positive, because you're approaching 0 from the negative side. And if this is getting more closer and closer to 0 from the negative side, this quantity here is getting closer and closer to positive infinity because we have a minus sign in front. And if t, let's say, so that's your parameterization for this new curve. As t goes to minus infinity, this gets closer and closer to 0. So this curve, if I had a second curve, let's say here's a question: if gamma tilde of t has z of t is equal to minus 1 of t, which of these domains would gamma tilde of t lie on the same side of the z equals 0 plane? All right, so that, for example, would be a question that's fair to ask. And in this case, right, I mean, from the rough calculation we did earlier, you'd have to choose this one. So that was sort of the gist of our first question, which was trying to analyze, given a parameterized curve, various forms, if it's nice, we wanted to deduce what it looks like. So if it's especially nice, we can actually get a pretty good approximation of what it looks like. If it's less nice, then you have to indirectly deduce what the shadows are, and it's limiting behavior to see if it's bounded or not, in what certain dimensions it's bounded, and so forth. On the same side, in this case, it means, is it lying on z greater than, in this case, right? We notice that this almost like this first curve must lie on the same side. Oh, shoot, sorry. I see what you mean. Same side as a curve above here. Sorry. Thank you in chat for that. right? So we figured out what side gamma of t is. Now I have a different gamma tilde of t. You know, what must the domain of gamma tilde t be so that it lies on the same side as my original curve of z equals 0. All right, so these are two methods, or a family of methods to deduce what parameterized curves look like. And then we ended last class, or the second part of last class, with how we might actually parameterize curves from intersections of surfaces, all right? Because in general, if you have an intersection between two, distinct surfaces of two dimensions, so each surface is two-dimensional in three-dimensional space, if they intersect generically, or in most cases, they're going to intersect along a line or a general one-dimensional curve. All right. So we looked at techniques in this. Given an intersection of surfaces S1 and S2, how can we parameterize the curve of intersection? All right. So that was the ending of last class. Well, we did one example of this. It was slicing a certain cylinder by a plane. And so now let's try something slightly different, which is where we left off last class. So last class, we looked at the following, right? We had the intersection of this surface, which we figured was a paraboloid, with y is equal to x. Now, in theory, you don't need to figure out this is a paraboloid at all. You could figure, you could manipulate this algebraically, which is what we're about to do, and figure out the intersection. But it always helps as a sanity check to see, if you know this is a paraboloid and you could have in your mind at least a shape that looks like this, and you know that this is a plane, and you slice a shape that looks like this, a surface that looks like this with a plane, you should be getting something that looks somewhat like a distorted circle or an ellipse or something like that. All right. So this is, strictly speaking, not necessary to have an idea of what these shapes even are or what these surfaces even are. But very often I would suggest whether you sketch it roughly on the exam or sketch it on a separate piece of paper, there's, it's nice to have a geometric intuition for what these surfaces are. So in this case, let's continue with this example. So last time, here's where we left off. Parameterize the intersection of the surface S1, which was 6y is equal to x squared plus z squared, and S2, which is a plane given to you by y is equal to x. All right, so I drew this last time. Let's draw it here more schematically. Right, so this is S1, and then we had plane S2. Right, so here's a curve of intersection here, or it should be some sort of distorted circular shape like an ellipse or something. All right, so visually, I hope you understand that if I have a shape that looks somewhat like this and a plane that looks like this, then you should be able to picture that its intersection ought to look something like that. So how might I do this? Does anyone have suggestions on how might I go about parameterizing this in the first step? So note that on the one hand, I need to have y is equal to x. On the other hand, I must also have this equation, 6y is equal to x squared plus z squared. So is there a substitution I might be able to make? Right, so if I try setting, or I guess substituting y as x, then the S1 equation gives the following. It gives 6x must be equal to x squared plus z squared. Now, what might I do with this? 6x is equal to x squared plus z squared. Right, all on one side, and what might I do with the x variable here? So all on one side, I could do x squared minus 6x plus z squared is equal to 0. And we could try and complete the square, x minus 3 squared. And this gets you a plus 9, so we've got to subtract off the 9 here, plus z squared, so 0. And then we get this. And now, what geometric shape is this on the x and z plane? Right, so it's a circle, and we could parameterize it. Where is the center of the circle, and what's its radius? So in xz, this is a circle centered at x and z is equal to 3 and 0 with radius 3. All right. And what sort of parameterization might I suggest, or might this be suggestive of for x and z? So I could write, let's say, I could try, say x of t, y of t, which we'll ignore for now, but let's do z of t. So what are x of t and z of t? What might they be? So some version of cosine and sine. In particular, what should be the coefficients, and are there any constants I need to add on this? Right. So it should be, say, z would be 3 sine t. Let's see. And what is x? Now the constant is going to be center coordinate. So if I'm centered at 3, 0, I have to put 3 in front of the x, and then I do plus cosine t plus 3 again cosine t. And now what should y be? What should the parameterization for y be? So remember, I'm lying on this surface and also this surface. So what must y be if I have these parameterizations for x and z? I must be equal, y must be equal to x. So at any point x of t, which is 3 plus 3 cos t, for me to be on the second surface, I must also be at 3 plus 3 cos t, right? Y's must match up, right? So let's go, you can parameterize this any, I didn't restrict how many times you want to go around this curve. So, you might as well put minus infinity to infinity. Doesn't really matter for this particular question. So that completes sort of the a second example of how you could compute the intersection between two surfaces. And really, this second example and also the first one is very limited in what you could do, right? In general, it's we know a few stock parameterizations in the sense that we always know how to parameterize a circle, in a sense. We know how to parameterize an ellipse, right? That was our first example last time. We just sort of modify the equations for a circle, parameterizations for a circle, such that these coefficients are no longer the same. So we sort of jerry-rigged that. In our case, now we know how to parameterize lines. We know how to parameterize straight lines. We know how to parameterize circles. We know how to parameterize ellipses. So conveniently for this course and WebAssign and things like that, a lot of the times these surfaces are going to be one of the quadric surfaces. So it'll be a cylinder, it'll be a paraboloid, it'll be a hyperboloid, and you could slice it with, you can intersect this with another paraboloid or another plane, and the intersection of any of those two surfaces, they're almost always, just by design, it's going to be like, if it's closed, it's going to be like a circle or an ellipse. Or in some cases, you might have something unbounded. If you slice this paraboloid vertically, it's going to look like a parabola, but we know how to parameterize parabolas. And so using these tools, these building blocks, you're able to parameterize a fairly large class of these intersections, so long as these surfaces are, of degree 2, right? They're sort of quadric surfaces. And so those are really the ones that you're expected to know how to explicitly parameterize. And the technique are all basically variations of this, right? It's almost always just some algebraic manipulation and completing the square to get the necessary form to apply the parameterizations we know. Okay, let me answer a few questions. Explaining y again, yes, the y has to be the same as x because you need to use this equation. Y must be equal to x. So whatever, we found what x, a parameterization that worked for x and z in particular. So we know what x of t has to be. So y of t must be the same as x. Would you be asked to restrict t? Yeah, I could ask you to restrict t so it goes around the curve once or twice. If I specify the question, then you should be able to do that. Okay, let's move on to slightly finer details of these parameterizations. So like I said, so far what we've done in this class, it's not, we're about to enter a section next week, which is slightly different. But so far what we've done is, it's a lot of physics inspired or motivated questions, right? So if you all hate physics, bad news for you. But this has been, traditionally very motivated by physics, in the sense that if you have a parameterized curve, then it's supposed to tell you, in essence, what the trajectory of a particle is in space, right? T, it's always, suggestively notated t because t is meant to be a time. So at time equals 0, you want to know where the particle is. At time equals 3, you want to know where the particle is. At time equals 100, maybe you want to know where the particle is. Now, associated to the movement of a particle, is traditionally in classical mechanics and things like that, it's been the quantities of velocity and acceleration, right? So we all know that, if you're driving in a car, your car traverses the road, which, if you're on the mountaintop, then this road is curvy and windy. So it's definitely not lying flat. It's honestly kind of a path confined to the mountainside, but it is in R3. It's in 3 spatial dimensions. And so as your car winds around this path, you could describe it theoretically by a parameterization for its trajectory. And then you might be wondering what your velocity of your car is at each point and what the acceleration of the car is at each point. Now, what do these correspond to? That's what we'll look at next. So velocity and acceleration. So given a parameterization, its velocity at time t is the vector given to you by taking the derivative of this, and it is, if you want to take the derivative of a function like this, the rule here is you just move the derivative inside, all right? So it's nothing very complicated. The reasons why you're able to do this is a bit technical, but I think you could find a reasonable explanation of it in the textbook if you're interested, but it's not going to serve much purpose in our class to know why at this point. But what you do is you take dx dt in the first component, dy dt in the second component, and the dz dt in the third component. And then the acceleration at time t is the vector, the second derivative of your parameterization, or in other words, the first derivative of your velocity. All right, and the speed at time t is just the absolute value of the velocity. All right, and if you want to write this out, this is going to be dx dt squared plus dy dt squared plus dz dt squared. It's all square rooted. Let me try and draw a picture for you of at least the velocity and speed. All right, acceleration is a bit more complicated to draw, but suppose I have a parameterized curve, gamma of t, then let's say at some time t here, I'm going to have my velocity vector, which is always going to be tangent to my curve, all right, in the sense that there's a vector in orange that looks like this, and that vector is precisely my velocity. So geometrically, what does this mean? If you remember that in one variable calculus, we had a graph, right? Y is equal to f of x, say, or in this case, let's call it y is equal to f of t, or I'm going to rename x as t. Then d dt of f, the first derivative at any point, is the slope of the line tangent to the curve. And so geometrically, if you look at this picture here, given a parameterized curve in 3 dimensions, in fact, this works in any number of dimensions, but focus on 3 dimensions here. I have a parameterized curve in 3 dimensions, and if I freeze the time at t0, maybe I should put t0 here, then the derivative of my parameterization is something called the velocity. Geometrically, it's a vector, and what does it give me? The velocity vector gives me the direction vector of the line that is tangent to my green curve here. All right, so at any single point in time for my parameterized curve, the velocity vector gives me the direction vector of a line that is tangent to my trajectory. Let me write this down. So geometrically, the velocity vector gives the direction vector for a line tangent to gamma of t at any t. Physically speaking, let's say you were driving along this windy road here. This is a path that your car is making. For technical purposes, once again, because it's physics, pretend everything's frictionless, all right? For whatever reason, you're in a car with rubber tires and somehow you're able to travel on a frictionless road. All of a sudden here, your car loses power. There's no more force on this car. There's also no gravity. Pretend there's no gravity. Then this line here is the trajectory that you're about to follow. If at this red point here, your car loses complete power, there is no more force acting on your car at this point, the line here, the straight line here, dictated by this direction vector, is the trajectory that your car is going to follow at that point. All right, so that's a physical meaning of this. All right, so maybe I'll write this down physically. Instead of a car, let's call it a rocket ship. So if gamma t is the trajectory, your rocket in space, and at t equals t0, your spaceship, your rocket loses power, d dt, your velocity vector, gives a direction you'll end up traveling in. Now, so this is, so you have 2 meanings of this now, right? You have a velocity vector here, and there's several meanings to this. One, geometric, it gives you the straight line, tangent to your green curve. And physically, it gives you, there's a purpose for this physically, which I've written down here. Let me do a couple more notes on here. So notational differences. Sometimes d dt of gamma t is written gamma dot t or gamma prime t, which would then be equal to x dot, y dot, z dot. So dot here is just an abbreviation for one time derivative. And the second derivative here would then be written gamma dot dot or gamma prime prime t. If gamma t is presented as a position vector, so this, your textbook does this a lot, right? It's presented as a position vector. R of t has x of t, y of t components as a position vector in Euclidean space. Then velocity is also sometimes written r dash or prime. I don't know what the notation of this is, as single quote mark t. Then acceleration is r with two dashes here. All right, so, or two slashes here. So that's just a notational. There are many notations for this, just so that you're aware of. They're fundamentally the same thing. Okay, let's do a practice here, which is let's now take the curve here. So we're going to look at this intersection, gamma t again, which we've already presented here. In fact, let me label this in green here. So example, consider the curve gamma t parametrized from the example here. What is its velocity, speed, and acceleration at 1, the point xyz is equal to 660, and 2 at any time. All right, so let's try and answer this. The first one, how might I figure out, well, the answer to the first one, 660. At what time does my curve pass 660? Remember, my curve here has parametrization given here, right? At t equals 0, well, maybe I should reverse the question of the procedure here. So at t equals 0, yeah, the ordering of the question is a bit wrong, but okay, at t equals 0, you're at the point in question. And so let's calculate the velocity. The velocity is given to you by differentiating each of these in t once. So you get minus 3 sine of t, minus 3 cos of t, or minus 3 sine of t again, and 3 cos t. So the acceleration here, we want to differentiate each of these again. So the acceleration is this is horrible ordering. I should have switched 1 and 2. I'm sorry, guys. Let me just put this down here for now. So acceleration, we're just differentiating this now. We're finding at any t, this, we want to differentiate these for general times first, right? So the acceleration, we differentiate what we had in the velocity once again. And what we get is minus 3 cosine t, minus 3 cosine t, and then 3 sine t. No, minus 3 sine t. And what we have now is, well, we could also calculate the speed. That's the magnitude of the velocity. This is the square root of this squared plus this squared plus this squared. So you get 2 times 3 sine t squared plus 3 cos t all squared. So you get, this is a 9 cosine squared t, and this is a 2 times 9 sine squared t. So you get one of the 9s coming out like so. And now at the point, so here's, I guess this is a bad ordering. I should have ordered this 1 and 2 and switched it. All right, so that's at general t. And now at 2, you want to check at what time your parameterization passes 660. Now, it might occur at several times, but you pick any time at which it passes through 660. In this case, I could choose t equals 0. And then you look at gamma 0 is equal to 660. Right, you could check this by plugging in 0 here and see that this is 6, 6, and 0. And then now you want to plug in 0 for every single one of these. So the velocity at this time is equal to sine of 0, 0. So this is 0, 0, 3. Its acceleration is equal to minus 3, 0. And its speed must be equal to 3. Okay, so we've done one example so far of calculating velocity, speed, and acceleration. Every other example with given parameterization is pretty much the same thing. Given a parameterization, you could calculate these quantities it's pretty straightforward depending on what particular parameterization is given. So let me now see what else we could use with this. So far I've given you, I guess, just the raw quantities of velocity, acceleration, speed, but I claimed earlier on that you could find a tangent line from these calculations, right? So here's the next example. Let's consider the same curve of intersection as before, so the one above. What is an equation for the line tangent to gamma, which is our curve above, at 660? So here I want the equation of a line that it's tangent to the curve that I had at a particular point. So how might I do this? So remember, we have velocity, acceleration, and speed, in particular at this point as well. So we know how to parameterize lines before, and in this case, we just want a line that goes through 660 and with the prescribed direction vector, right? So this line, if I wanted, the easiest way to write this, right, is perhaps just to make sure at time equals 0, I'm at the point 660. So I just do 6 plus the direction vector at this point. That's my velocity at this point. My velocity is 0, 0, 3, so there's nothing in t. 6 plus another 0t. And then at the point 0, it's 3t, right? Now let's do the same thing with it. Well, the same curve. I guess find an expression for the arc length of the curve of intersection in the above. And let me just remark here, we've seen an expression for arc length previously in 2 dimensions. And the expression is, the expression was, if you have a curve and you have, and you want to find the arc length of this curve, then for any parameterization of the curve that traverses your curve once, you want to integrate the speed over the interval of your parameterization. So recall, this is the same as in R2. If a curve L, so given a curve in R3, its arc length, or just length, is given by the following. So the length of L is equal to the integral of its speed, where x of t, y of t, z of t is any parameterization that traverses L exactly once. Okay, so here I'm asking for the arc length of a curve of intersection in star. So let's remind ourselves that we had a parameterization here, right? Our curve of intersection way above here was this turquoise curve here, and we figured a parameterization could be of this form. So recall, so in this case, we had this parameterization. Now, I didn't really care about the interval or the domain of this parameterization earlier. I said, I didn't specify whether I wanted to go through it, how many times I wanted to go through this path. But if I wanted to find the length of this intersection now, what should I do to make my life easier? How should I restrict the domain of t in this case? To make sure this traverses the curve once, I should restrict t between what and what values? Right, I could do 0 to 2 pi, 2 pi to 4 pi, minus pi to pi, any interval of 2 pi. So I could try 0 to 2 pi, or any interval of length 2 pi. And why? Well, we want this to encompass the entire curve. All right, and that's with our parameterization here. It's easiest to see this in the x and z shadow. If you just look, remember along xz, this is really just, or xz it really is just a radius 3 circle. It's kind of off center, but for you to go all around the circle, so for your actual curve to go all the way around, then certainly if you just look at the trajectory and how it traces out a shadow, its shadow must also go all the way around. And in this case, it has a circular shadow, and so you have to go all the way around the circle. It's 360 degrees or 2 pi radians. All right, the same reasoning works for an ellipse, right? If you have an elliptical shadow, you have coefficients in front of cosine and sine in a pair of these variables. Even if the coefficients don't match up, you need 0 to 2 pi to go all the way around. You can have variants of this where, if you have a circle, let's say if you have an honest to God circle, that's x of t is equal to 3 cos t, and let's say y of t is, or let's say z of t is 3 sine t, and y of t, let's just ignore it, it's just 3 or something. Okay, there's none of this. This is just a circle that's at height y, or along the plane y is equal to 3, and it's a radius 3 circle, 3 cos t, 3 sine t. All right, and if you want just the length of, say, half this circle, a semicircle, well, you know it was just like pi r squared over 2. But if you didn't know that, you could also set this up in terms of this integral here. But the bounds here would be 0 and pi, for example, because you just want 180 degrees or half the circle, right? So you could adjust these parameters to see what portion of the curve you want to measure the length of. Just make sure if you want to go all the way around, if you want to make a full circle, then you have to go 0 to 2 pi. So that's sort of the key point here. So the arc length of the intersection, this is given to you by the integral from 0 to 2 pi of the speed, right? This is a speed, and we found what the speed was. The speed is given by this expression, 9 plus 9 sine squared t. Well, square root of that. So this is, I could factor the 9 out. So that's 3 times 1 plus sine squared t. So now we've seen a couple of things we could do with, with speed. We could really calculate the arc length or how far you've traveled, but this geometrically kind of makes sense, or physically as well, right? If you have a speedometer on your car, in theory, at each point in time, you read off the speedometer on your car, how fast you're going. And then, depending on the time that elapses, is there A to B, how far you've gone from A to B, right? You just, you integrate over the speeds. If you're a constant speed, then that's just B minus A times the constant speed. So that's not very surprising. And earlier we found the tangent line to a curve. And now there's one thing that we could also do with a tangent line to a curve, and that's to find the angle of intersection. All right, so once again, let me address one of the questions earlier on in chat. The way you got the values of the tangent line to the curve is at any single point on your curve, you want the line starting at that point with the direction vector given to you by your velocity at the point. All right, so in this case, you're starting at 660, and you want to add to that t times the direction vector, which is 0, 0, 3. So that's how you get this. And one thing that helps you with is to find angles of intersections. All right, so here's an example. Well, let's just make a definition. If two curves, let's C1 and C2 intersect at a point P, then their angle of intersection is the angle made by their tangent lines at P. Okay, so here's a picture. I have C1 and I have C2. Then along C2, they cross at this point, so I have the tangent line L2. And at the very same point, I also have a tangent line here, L1. All right, and I could measure the angle here between these lines, theta. And that's the angle of intersection at the point P. All right, I should say, unless I specify, I would specify the acute angle of intersection if that's what I'm looking for, and that's what I drew here. I believe on your web assignment, if it asks for this, they automatically want the acute one. All right, I will specify in my test if I want the angle to be acute or not. Right, in general, you could also argue this is also a valid angle for intersection. I don't make the distinction unless I specifically ask for it, but your web assignment would probably want the acute angle, okay? Let's do the same curve of intersection in star. It's the same curve we've been working along all this time. So what is the angle of intersection with the line L of t is equal to 660 plus t times 1, 2, 3 at the point 660. So let me remind you, because I guess it's way up in the page here. We have the following. We have our tangent line was this. So let's say, recall, this is our tangent line to our curve at 660. So what might I do? Well, the direction vector of this tangent line was our velocity at 660, right? The direction vector, 003, was our velocity of our curve at 660. So what dot product should I be taking here between, what dot product should I be taking in order to get something, the cosine, say, of the angle that I want? So we have 1, 2, 3 dot 003. That's almost true. What should I do to each of these vectors to actually, honest to God, get the cosine of the angle? So without any coefficients in front of the cosine. So recall, we have this formula here where we have, let's say V1 is here and V2 is here, right? Then, you have the angle between them, like so, then you have this formula here. So if I just want to isolate the cosine, and eventually take arc cosine of whatever is here, it benefits me to divide out by their norms, right? So I want to normalize. Let's say let V1 be my velocity, 003. Let V2 be the velocity, in this case, of the tangent line to this line I'm intersecting, right? That is, this line has direction vector 1, 2, 3. So v1, if I normalize, this just gets me 0, 0, 1. The second vector gets me 1, 2, 3 over the magnitude of 1, 2, 3. And that's 1 squared plus 2 squared plus 3 squared, right? So that's 14, root 14. So this means that theta, my angle of intersection, is going to be arc cosine of this dot product. And that's precisely equal to 3 arc cos of 3 root 14. All right, so let me recap. We had a curve above that unfortunately you can't see in this page anymore, but it had a tangent line here, right? At 6, 6, 0, we calculated above that our curve had this tangent line. Furthermore, the reason we got this was because we knew the velocity of our curve. The velocity of our curve at 6, 6, 0 was 0, 0, 3. So I knew the velocity vector of my curve at 0, 0, 3. And I also know the velocity vector of the curve, or in this case, a line that's intersecting my curve at 6, 6, 0. And note that the velocity vector of any line is just the direction vector, right? d dt of this gets me 1, 2, 3. So I have the velocity vector of my original curve, which is 0, 0, 3, at the point of intersection. I also have the velocity vector of my intersecting curve at the same point. That's 1, 2, 3. And what I need to do is normalize both, right? I normalized the first one, I made it unit length, and I also normalized the second one, made it unit length. And then arc cosine of their dot product is going to get me the angle of intersection. So there's one geometric quantity that's very useful in this case. You'll note that our procedure here really just, it didn't quite require my full velocity, right? In fact, I needed to divide out my velocity by its speed, by its magnitude, right, to get its unit length. What we had here was a velocity at a point divided by its magnitude, by its speed, in order to get some vector with a direction, but its unit length. And really, it was this unit length vector that got me all the geometric information of my crossing of these lines. All right, so here's another definition that's useful. Okay, given any curve in R3 with parametrization gamma t, its unit tangent at any point on your curve is this vector here. It's also notated with boldface t. And it's just your velocity vector divided by its magnitude. And what does this give? Well, from above, we know that this is a unit vector giving the direction of the tangent line at gamma t. Now, visually speaking, what could we say about the uniqueness of this? So let's say I have a curve, gamma. Notice I'm not telling you what parametrization this is. I just visually drew on this piece of paper on the screen curve. And I put a point on this curve here. Maybe visually speaking, what might you expect? How many tangent lines could I draw through this point here? Is there no tangent line? Is there one unique tangent line? You know, how do I have a line that is just uniquely tangent at a point? It seems like, you know, and perhaps it takes a little bit of thought and proof, but it's reasonable to say that geometrically speaking, there is a unique tangent line here at any point, right? So it seems like, you know, for any given curve here, I could put a lot of different parametrizations for the same curve, right? And the velocity seems, you know, depending on how fast I traverse this curve, the velocity is going to, you know, be different depending on parametrizations. But this unit tangent vector here is actually independent of parameterization, just like arc length, right? Remember when we look at the arc length formula in 2D especially, I told you as a fact that the length of any curve doesn't actually depend on your parameterization of it. So long for arc length as your parameterization traverses a curve exactly once, then it doesn't matter what particular parameterization you choose, the arc length always gives the same number. So that's kind of independent of your parameterization. Now, in this case, I'm claiming that the unit tangent vector is also unique from parameterization up to a sign, right? This is t here, that's your unit tangent vector. Or you could flip it, maybe t is pointing this way. So the unit tangent, t, is independent, that's not how you spell independent of parametrization up to a sine. I guess I say the unit tangent t up to sine is independent of your parameterization. I could put any parameterization of this line of this curve I want, but if I calculate the quantity, the velocity over its speed at any point here, it's all going to lead me to the exact same vector, or maybe I'm going to flip this and if I parameterize this backwards, I'm going to get t, but pointing the opposite direction. But it's always going to be either this one or the other one. So in a sense, the unit tangent vector is a truly geometric quantity. It's independent of how you describe your curve. It just is naturally associated with what the curve looks like. All right, doesn't matter how you place the curve inside, how fast you traverse it. Okay, let's do one more example to round this off. Consider curves. Gamma 1 t is given to you by t squared 4 minus t, 5. Gamma 2 is 4, t plus 3, 8 minus t. The first thing is, do these curves intersect? If particle A, okay, so let's say if gamma 1 of t is a trajectory of particle A, and gamma 2 is a trajectory of particle B, do they collide? And 3, let's find the cosine, the angle of intersection. So how do we find if these curves intersect, or how do we know if they cross each other? So what happens, if these curves do cross each other, what happens in the x-coordinate? Well, we need to check solutions to the following. In x, you want t squared to be equal to 4. And in y, what do you want? Right, so maybe I should label this t0 and t1 again, or maybe t1 and t2, because these curves are t1 and t2. Right, this curve is gamma 2. So let's call t1 the parameter for gamma 1, t2 the parameter for gamma 2. Then they don't have to necessarily arrive at the same point at the same time. That would be a collision of particles. But they must arrive at the same point at some time. So you want 4 minus t1 to be equal to t2 plus 3. And then you want 5 to be equal to 8 minus t2. Okay, so what does this first equation tell you? This tells you t1 must be equal to plus or minus 2. Now take a look at this last equation. Right, this last equation tells you t2 must be equal to 3. So the middle equation, so if t1 is equal to plus 2, right, we have two options for what t1 has to be here. If it's equal to plus 2, then 4 minus 2 is equal to 2. And at t2 equals 3, this is at 6. 3 plus 3 is equal to 6, and 6 is not equal to 2. So that's bad, right? That means that at t1 is equal to 2 and t2 equals 3, we can't solve this. So certainly, that's whatever this is, there's no intersection point corresponding to x equals 2 and z is equal to 6. All right, however, if t1 is minus 2, then 4 minus 2 is equal to 6, which is equal to 3 plus 3. So this is good, which means the intersection, or the crossing, is at x is equal to 4, z is equal to 5, and y is equal to 6. And these x equations are because, well, this is x, this is equation for x, and you want x to be at 4. So this is x at 4, z is equal to 5, y here, you figured out that this has to be equal to 6. All right, 2, do the particles collide? What's the answer here? So we have a no and a yes. So what does it mean for them to collide? Well, you need it, instead of solving this system here, you need t on both sides. You need t1 to be equal to t2. But in this case here, well, even these options, none of these options are 3, so you could immediately say that they do not, right? To collide, you need t1 to be equal to t2 and arrive at 465. That's not. By the above, you have at 465, you have t1 is equal to minus 2, which is not equal to 3, which is what t2 is. So they do not collide. All right, we're out of time today, but take a look at 3 and we'll reconvene.